more, and this notion of 1 of k coding. And then I went on and said that there are essentially 2 types of methods for classification. One that's based on probability, and the other one not based on probability. And logistic regression and LDA are probabilistic based methods, and in that method, in the probabilistic method, the most important thing is to model the conditional probability of the class given the data. That's the most important thing. And I'm trying to motivate this conditional probability of the class given the data. So I define this thing called the risk. Risk is essentially the average test error. It's the test error, not the average test error. It's the test error, okay? And it's called risk. And based on this risk, we would like to find a class, I theta. I theta of I star is the index of the class. Index of the class. Okay? And what we're trying to do is to minimize the risk. We want to find the class that minimizes the risk. And then that led to minimizing the posterior risk. Okay? Posterior risk. So I'm continuing on. Okay, so let's look at a particular case for a loss function. Okay, a loss function that is defined as such. The I here, so the loss between, so I hope students like sometimes write loss as f theta x I y I. Okay. Or here I've written it as class ij. Same thing. Yi is the label, ground truth. Yi will be one of the classes. And let's say Yi is Cj, class Cj. Okay? From C1 through Ck, it's Cj. Okay? And your prediction based on xi, right, you're going to find this function f, which is parameterized by theta. We've been using this notation. It takes xi and produces class Ci. Okay? So that's the loss function. It's the same thing. Okay? And I hope people are not confused by this. Now, when that loss function is defined as this thing right here. I here represents the indicator function. I indicator function. Or sometimes called the 0-1 loss. Whatever this is, it takes on the value 1 or 0 when A is true. When A or otherwise. 0-1 loss. So when Ci and Cj is not when Ci is not equal to Cj, when that is true, it takes the value 1. When Ci equals Cj, it's equal to 0. Okay? That's called the 0-1 loss. 0-1 loss, or another way of indicator function. Okay? That's all it is. So let's look at the posterior risk of this. What is the posterior risk? Posterior risk is, so it's over all conditional probability given x. Okay, so your posterior risk is given x, and let's assume it takes the class Cj, okay, and that Cj can be any one of the classes, C1 equal to Ck, right? X can take any one of the classes that we want with certain probability, okay, C1 with this probability. What is the loss? The loss is 1 minus, the risk is 1 minus this loss. So it's 1 minus, what is this? When your prediction is Ci and Ci. I'm evaluating the risk, this posterior risk for class Ci. Okay? So one of them is Ci. Your prediction is Ci. But ground truth is Cj. And that happens with this probability right here. Okay? So 1 minus that is sort of the opposite of loss. Okay? I want to find this I class that minimizes this. Okay? So what is this value right here? I'm going to plug in for all values of j. Okay? So if I plug in for all values, if c equals 1, let's say, I'm just writing this over again. This shorthand. So let's say there are, let's assume that there are k 3 classes. So I'm looking at Cj equal 1, 2, 3. And that will be 1 minus. And I'm going to look at Ci. Cj. And probability of Cj. Let's say your Cj is not equal to 1, so that this will be 1 minus L Ci C1 equal to C1 plus 1 minus L Ci C2. Okay, there are 3 classes, so do that, right? Now, what is this value? If I, so let's say I is equal to 1. If I equals 1, then this value with I equals 1, then what is our C1 x? What is this value? What is this value if I is equal, so it's going to be 1 minus, what is this? It's going to be 0, TC1 x. The second one will be 1 minus 1 TC2 x plus 1 minus 1 T. And what are we left with? TC1 x. Right? So, that's for I equals 1, and you would assume that for I equals 2, it will be a conditional probability of C2 given x, and when I is equal to 3, then it will be conditional probability of C3 given x. So, what we are left with, I star equals that. So, the conclusion here is minimizing the given 0-1 loss, meaning that if you get it right, you get no loss. If you get it wrong, you get 1 loss. Okay? If you have that kind of a loss, minimizing the base risk. What is base risk in other words? Minimizing the test error. Leads to a classifier that maximizes the conditional probability of the class. So if I'm minimizing, if I have 0-1 loss and I want to do best in terms of that loss, what do? I find the conditional probability of for that x, and then I choose the class that maximizes. So I choose the class that maximizes, that has the highest conditional probability, and that seems obvious. Okay, so what the goal is to find this. Find the conditional probability of the class given the data. Okay, from data. So this is a very important point. Okay, why do we? So this is the reason why we do. There are 2 methods. One that's based on probability tries to model the conditional probability of the class given the data. Okay? I cannot emphasize this enough. This is a very important probability. If you can accurately estimate the conditional probability of the class, then you're done. You cannot do better than that. You cannot do better than that. That's the best we can do. Okay, having said this, let's move right on to logistic regression. Another word for logistic regression is log linear model. Okay, log linear model. And I'm going to assume this simple case of two classes. So, class 0 or class 1. Or class 1 and class -1, labeled -1. Okay? There are only two labels. Now I'm going to look at the log ratio of the conditional probability of the two classes. Here it is. So I'm competing, I'm making a competition between these two classes. Class 1, class C1 and class C2. And I'm looking at the log ratio of that. And I'm going to model that. So, and the other class, you can write it in terms of, so you can write the conditional probability of the class C2 as 1 minus that, right? I'm going to assume this ratio is linear. Ratio is linear. Now, if this ratio is equal to, let's say, A, or linear, so I could write down PC1. PC1, I could write this, I could make PC1 the subject, and it leads to this conditional probability. And what do we call this conditional probability? Okay, it's in the 2 exponential form. Okay, we call this a sigmoid function. We do this, and this is called the sigmoid function, and we've defined this thing as I want to make this. What is the decision boundary between these two classes? Let's say x, this x, is x1, so here's x1, x2. What is the decision boundary? What is the decision boundary? What is the definition of decision boundary? When the conditional probability of the two are the same, right? Where is that? Pardon? In general, right here. Where is the decision boundary? There's two classes, okay? I'm looking at the ratio. I said that this is, so if I'm minimizing the base risk, or I want to minimize the test loss based on 0-1 loss. Okay, we normally think about 0-1 loss, right? Looking at this and looking at the ratio, where is the decision boundary? What is this, 1/2 to 1/2? When this is equal to 1, when this is the same. So what is the decision boundary? A is equal to 0. So what is the decision boundary? It's a line. It's a line. It's a line. That's what I'm trying to say. What is this? What's the function of this line? So yes, so it's this. It's simple. I don't ask hard, difficult questions. It's a line. Okay? And look, I did this math, and I found the conditional probability to equal to this form. And I call this thing a sigmoid function. And I think I defined what sigmoid function is before. So if the conditional probability of one of them is a sigmoid function, then what is the decision boundary? What? When I model this conditional probability as a sigmoid, where the exponent is a line, what is the decision boundary? So forget about all this. When I model this as such, like that, in this form, what is the decision boundary? It's a line. That's what I'm trying to say. I started out with a line and then it came to a sigmoid function. I'm asking you in a different way. When I model the conditional probability as a sigmoid, what is the decision boundary? It's a line. When the conditional probability is a sigmoid, it's a line. That's what I'm trying to say. Okay? And it's very important to have this decision boundary. Once you have the decision boundary, then you have the classifier, right? Then you have the classifier. So if one of them is sigmoid A, where A is defined, if I define this thing to be this, then the other one will be sigmoid minus A. Okay, you see, understand my logic right here? I look at the log ratio and we say, oh, it's a line. And I did some math and I found the conditional probability to be a sigmoid. Sigmoid with the exponent being a straight line. And I'm asking you in a different way, when the conditional probability is a sigmoid, what is the decision boundary? It's a line. It's a line. Okay? And why am I looking at the conditional probability? Because if my loss is 0-1, the best test error that I can get, the classifier that minimizes the test error, is what? Is the conditional probability, maximizing the conditional probability, right, of the class. You cannot do anything better than that. You cannot do anything better than that. You understand my flow? Okay. So, a little bit definition and so logistic sigmoid function. We call this thing logistic sigmoid. What is a sigmoid function? So it looks like this. Oh, you said this is a sigmoid function. How come this is a sigmoid function? Well, if I multiply by the exponent of minus a up and down, then I get that. It's the same thing, okay? Logistic sigmoid function. Okay? And if the other one is sigmoid a, then the conditional probability of the other one has to be sigmoid minus a. Why? Sigmoid a, the other one has to be sigmoid minus a. Why? It has to be equal to 1, right? Given the data, it's either class 1 or class 2. If you add those two. Okay? And another word for A, in terms of the sigmoid, we call it the logit function. Okay. I'm sorry that there are so many definitions, okay? But it is what it is. Okay. I wish this field started out with some minimum terminology, and everyone used the same terminology. It didn't happen this way. We had lots of people from different groups. One from statistics, another from computer science, one from physics, and they found out that they were doing the same thing, but they were using different terminologies. And they got together and became machine learning. So there are so many terminologies here and there. So, that's logistic. Logistic regression is modeling the classifier as a signal, LR. Okay, and what is the decision boundary in the logistic regression? It's a line. Okay, let me emphasize this. Now, let's look at this. Let's assume that theta is, I've defined this theta as the bias and this other term, okay? So, it's a vector. It's all vectors of the parameter that define the class. P plus 1, and there's the bias. And I'm going to assume the data in this form. So I'm given the training data, x, y, and I'm going to put a 1. So I'm given training data, which is weight of a person, height of a person, and let's say gender. But rather than using it this way, what I'm going to do is add this. Okay, sorry about this. I should be using transport. So if I'm doing linear regression or linear classification, how would my prediction, what would my prediction look like? And I call this X. Call this X. Linear classifier. What would be the mathematical form of the linear classifier? Two classes. If I write it in this form, it will be linear classifier, come on, linear classifier would be psi of what? That's a transpose X. That would be my linear classifier. I can write it simply like that, putting in the bias. Okay? Now I want to look at this. I'm going to try to minimize the likelihood. Okay? So different. I'm going to try to minimize the likelihood. Okay? Likelihood. So L here is going to be the likelihood. Okay? And I'm going to look at the log likelihood. I want to find my theta such that it minimizes the log likelihood. Why am I doing this? Why is my professor, instructor, okay, you've defined logistic regression now, okay? It's in this form. Why is he talking about likelihood? Is he trying to confuse us? What's the next step? It's modeled this way, okay? Logistic regression. What do you need to find out to do logistic regression? Yes. Oh, I'm given data. I'm given data, right? Okay, I'm going to model it this way. How am I going to find my theta and theta naught? That needs to be determined. In what way am I going to model theta and theta naught? Right? In order to use this. Understand? Okay? Why? So, the next page is about training. How do you find your theta? How do you find your theta? So in order to find your theta, you have to have a standard, right? You have to have some type of criteria to find your theta. Everyone understand what I'm saying? Okay. You know, it's and what is my criteria in finding my theta? What is my criteria? I want to find my theta that maximizes the log likelihood. What does that mean? What is likelihood? Likelihood, okay, likelihood, it's probability of the data given the parameter. This is likelihood, right? But we should be really thinking about conditional likelihood, as I said. This is, and if you remember, we have data, which was data and data is it's the input and the output. So which one should you? I want label given input. So let me just your parameter, any parameter that you find should be a parameter that is a good representation of the data, right? Should be a good representation of the data, that observation that you get. Wouldn't this be a good criterion? For given some parameter, I want the probability of observation. This is, I should say not data, I should say observation. Probably that's a better word. What observation do you have? What observation do you have? It's only the training data that you have. That's the observation, right? I want to find theta that maximizes the probability of that observation. Isn't that a wonderful, I mean, what other criterion can you think of? Right? Maximizing the observation, probability of the observation given the data. Observation. And what observation do I have? I have data and the label. Which one? I want to maximize the probability of the label given for some input and some parameter. Wouldn't that be good? Finding that theta in the logistic regression. Can you think of anything else? Very good criterion. Log likelihood, by the way, log likelihood and likelihood. Okay, max, finding the position, finding the theta, finding the position that maximizes the log likelihood and the likelihood. The position, you think it would be different or is it the same? I have a likelihood, okay? I have probability. I'm going to use this now. You know it's maximum there. I'm going to look at log of this. Can you tell me something? Where the maximum is going to be the same. It's, I don't know, it's log, so it's probably going to be looking similar shape as Why does this happen? Why is it the same location where it's maximum? Why? Yes, because the log is what? It's a monotonic increasing function. It's not going to make it's not going to make this one go up like that, right? It's monotonic. Everything is monotonic. So instead of looking at the likelihood, I'm going to look at the log likelihood. Why do I want to look log likelihood in this case instead of the log? Instead of just the like. Why do I put this log in there? Independent, okay, the log, okay, that's another thing. Another, what's? So the right here, I say label, but here, what is the label in here? The class. And what kind of a function is this all in here? It's made out of what? Exponential. So if you put log in there, it'll turn it into sort of a polynomial type of thing. Okay. So, we've been considering two classes. So what are the labels? There are two labels that we're going to place. Okay? The label is either going to be 0 or 1. Okay? 0 and 1. It's either one of those things, right? So here it is. For class 1, it looks like that. For the other class, it's that. Or I could write it this way. What's another way of writing it? Minus. No, I should change the notation. I want this thing to be a column vector. I want this thing to be a column vector. It's written in a row vector, but it's column vector. Okay, there's a minus sign. Minus. Okay? Why am I doing this again one more time? To find the parameter of the classifier. And what does logistic regression give you? The model. I'm going to be using sigmoid as one of the class. That's logistic regression. And what is the decision boundary? It's a lie. Okay? So now here it is. Log of the likelihood. Log likelihood, we call that. Log likelihood is a function of theta. And it's written like that, but I want to, for those of you, how do you get that? I would start with the basic, really basic. Probability of y1, yn given x1, xn, and then there's a log. Right? That is the original definition of log likelihood. Log of this. Now, I'm going to write this thing. I'll just here. So log of probability y1 is equal to log of probability of y1 given y2 yn times probability of y2 given y3 yn You might say, what the hell is he doing right here? Okay? Let me just show you. It's easy. I'm going to look at probability y1, y2, y3. Just space there. Is equal to probability y1 given multiplied by probability 2 there. Right? Probability 2. Is this true?
Yes.
Think of this as, we know this, right? We know this. y1, y2, this is equal to probability y1 given y2 times probability of y2. What rule is this? What rules have I used? Huh? Conditional, well, I mean, it's sort of chain rule or Bayes rule, written in a different way. Bayes rule, we know Bayes rule. Using just y1 given y2 is what? Probability of y1, y2. Oops. Oh, where is it? Right? So I'm moving that away right here. That leads to that. Right? So everyone's not surprised. Oh, I know this. This is too easy. This is easy, right? We already had this. Let's move a little bit. Now consider that this 2 thing as y2 before. Then that, right? Right? And then what have I done in my third step? I split this up, this base rule one more time. And I think from probability, basic probability that you learned, this is called, say it again, Markov chain. Markov chain, right? Now let's look at here. Look at here. So I'm going to really lot of detail. Okay? So that's why I'm going slow, I guess. Ignore this now. Okay, from here, I did this. I left the space here. Now, y1, y2, y3. But all of this was performed given some world. What world? World of x1, 2, and 3, theta. How do I do that? What do I mean by that? So everyone understand that this is easy. This is easy. One more twist. In this world of x1, x2, x3, and theta. In this world of x1, x2, x3, theta. In this world of x1, x2, x3. For all of this, that you said it was easy, I'm going to put it in the given. And it will be correct. Given. Just put it in the givens. 이해? 문제 없어? Good. And that's what I've done here. It's generalized to n. Markov chain, and put given. Now, this thing can be reduced. Conditional probability of y1. Is that dependent on y2 or yn? No. I could throw away all of that. Because y1 is independent, it's not looking at y2. It says, what was the label? What label did you get for x2? It's not asking that question. It's all independent. And what's left here? And what's left here? So what we're left with log of product of p, y, I, x, I Just waste of time, right? Then log, and so I got that. Okay, just a little bit of detail, but just so that you understand how I got that right away. Okay. Now, oh, this is great. This thing right here, you can write it like that. This is mathematical ingenuity. What? What is this? This is the conditional probability when? When? One. When? What about this one? Oh. So how can I? What is that? When yi is equal to 1, if it's 1, then this one is there, but the other one is what? 1 minus that. And what is that? 1 minus 1? 0. So what does that become? 1. So this one is switched on. When yi equals 0, what happens? This one becomes what? 1. And this becomes what? 1. It's like a switch. Depending on what yi is. On and off, on and off. Oh, it's incredibly good. Nice way to write, you know, if yi is equal to that, then it's this. When yi is equal to z, it's equal to that. In one equation, you write it. Ooh, that's nice. What's another benefit of using this formulation? Why do we want to write it like that? Low value? You can get log value, but what am I getting at? Why do I write it this way?
It's like a very general.
What am I going to do later on? What am I going to? I'm going to define log of likelihood. How is theta going to be obtained? I'm going to maximize this. I'm going to maximize this, right, to find my theta. I want to find a theta that maximizes this. Can I take the derivative of this? Yes. If yi equals that the sentence. If yi is equal, or else, if it's two sentences, then taking the derivative, it's a little bit complicated. But if you have it in one equation like that, easy. Wow. Wow. You should be awakening right now. So I put in the definition for these things. Take the log. Taking more of that, and I get that. I want to maximize this to log. Okay. Still, it's not easy. Why is it difficult? If you take, I mean, we want to take the derivative, and we want the left-hand side to be. You want this to be not a function of. So you take the derivative and you want to set it equal to 0. And then you want the theta term to be on the left-hand side, and on the right-hand side, just the x's. Wouldn't that be nice? You take the derivative of this function, you want to manipulate it so you get x only on the left-hand side, and you want to get the right-hand side in terms of, not in terms of theta, but x's. Wouldn't that be nice? Oh, you would want that, right? You would want that. Well, let's have a look. Take the derivative, then you get that. Ooh, it's ugly. A little ugly. How am I going to put theta and set this equal to 0? Not easy. I can take one more step and say, okay, what is this? What is that? Probability that it's equal to 1. 1. And I could take out xi. So I want my theta to satisfy this. The thetas are all in here. The thetas are all in here. Theta. Thetas are all in here. Very difficult to get an explicit form. And you have to, you solve this by some iterative reweighting equation method called the Newton-Raphson. What is Newton-Raphson's? Have you heard of Newton-Raphson's? What? In high school, never heard of Newton-Raphson's? Newton's method? What is this? Maybe if I sort of give you a figure, so here it is, x, and let's say I had a function that looks at y equal fx. Let's go out a little bit. Like that. And what am I trying to find? Right, that point right there. So you start with, yes, I think you know, you've seen it. You start with some initial point. Oh my goodness. So while I'm doing this, we're a little bit behind in class, but I want to explain sort of like the details, okay? And that's why we're going slow. So I hope you don't criticize me for being slow. Okay? So we may not finish all of the topics that we've covered. Okay? Anyways, let's see. Newton's rational. So I start with x0 right there. So x0, and I find f x0. And I put a line here. Is it fitting a line here difficult or easy? What point does it pass through? X, fx0. And what is the gradient? F of x at x equals. Is that difficult? No. Finding that point, is that easy?
Yes.
I do that one more time. If I do that iteratively, would I be able to find x star? Yes. That's Newton's law. Okay? So we'll have an extra problem dealing with this. I don't know if the homework included this, but I'll give you an example. So it's an iterative method to find theta. And there are right now lots of routines to let you find this. And it turns out also very important is that in the formulation that we've used, the first element, or x0, was 1, right? Remember, I put a 1 right. I put a 1 right here. Right? Everyone remembers that, right? And you know why I did that? To get rid of the bias and put it in the theta. Right? The summation of the yi's have to equal this probability. Why? Why do you think this has to be? Why? Why? Hmm? F0 is 1. Put it in here. Put it in there, and you get that. Okay, so he got it. Oh, okay, that's good. Yes.
But are we sure that it will only take reasonable amount of iteration before it converges?
Reasonable. I don't know what you mean by reasonable amount, but You know, it depends on, I don't know what the convergence rate is. Okay, I don't know what the convergence rate is. I'm sorry about that. I'll try to look that up.
And also uses this method for example one solution, but what about like others? Should we start from different points to find different solutions?
Yes, if, would you have multiple solutions? When would you have multiple solutions? That's a very interesting point. I really haven't thought about that, but yes. Would you have multiple solutions in this case? Is it convex? What is, I mean, I haven't talked about convexity, but yes, is this convex? Those are interesting problems we can work on alone, okay? So that's good. That's good. But there is only one solution. This leads to one solution, not multiple solutions. One solution. Okay. Now, yes.
What if there will be plateau?
Plateau? You mean flat or?
Yeah. So it's not this. So when you do this also will be zero.
No? Flat?
Yes, like not the maximum, not the minimum.
You know, we are trying to find, so, you know, we've changed this problem to this. Finding the zero, the derivative, we want to set this thing into zero. So it's not, so we want to maximize this. That turned it into a problem of finding the root of the derivative. Finding the root of the derivative, right? Derivative equal to set to zero, right? So, do I run into complications? I've not thought about that problem a lot. I'll have to look at it. I want to give you the, you know, correct. I want to tell you the correct things. I'm not 100% sure about that. Okay. Yes.
So you say we only have one solution for that.
Yeah.
So it means it only crosses the x-axis only once.
Crosses the x-axis, yes, once, if that's the solution, yeah, for this one, yeah.
So it means that it is guaranteed to be monotonic.
It's guaranteed to be
Otherwise, it
monotonic.
will cross the x-axis more than once.
Yes. Yes, yeah, that's, would be the correct statement to make. Okay. Yes. Okay, another thing, it's 10:15, but I just want to say this and then sort of, if I have multiple classes, okay, we dealt with two classes. Let's say if I had multiple classes, then what should be the model? The model that we use would be called the normalized exponential or softmax. It's an extension of the logistic regression. That was two classes. And if you look at it, the top is in an exponential form, just like the condition logistic regression we saw, and the bottom is normalized. So when we add up all the classes, what is it going to be? It's going to be 1. Okay? So in other words, also, in the exponent, what was at the exponent of the logistic regression? It was a linear function that was better than theta, right? There will be a parameter for each of the classes, the theta. So, let me just, oops. Class 1 would have this parameter. Class 2 would have its own parameter. Class 3 would have its own parameter.
There would be some different tetras for each class.
Well,
For
it's the same x for the same x,
Yes,
but
different
different parameters for each of the classes. K different, not K different. Oh, you mean K different classifiers? I guess you can sort of think of it that way. You think of it that way. Okay. So extension of that will be, yeah. I don't want to say that. And I will continue on from there. From that. Okay. Okay. So some of this probably will be in your next homework 4, implementing. Okay. Training logistic regression. Okay. Using Newton's method. So it's 10:19, so I stop here. Any questions? So the homework, I've updated it. Problem 4, there were some typos. So I've corrected some of them and uploaded it today, this morning. It was only problem 4, so I hope no one is going to be penalized or, I don't know, lose time. Because of that. It was only problem 4. Okay, so I stop here. Look at the projects. Okay? The projects.
What about the final report that you
So as I said, we're probably going to have a leaderboard. Okay? So you upload the performance, right?